Okay, and let me start my sharing. Okay, I seem to have lost my sharing option. That's right. Okay. I hope you're able to see the screen share. Thank you. Okay. So we will, as usual, begin with our customary namaskarams to our gurus. Shri Guru Bhyo Namaha. To our gurus.
Can we put it on presentation mode?
Yes. Namaskarams to our gurus, Swami Dayanand Saraswati ji, Jay Kumar ji, and Raj Vedam ji, who have been the inspiration for this course. Right. And let us also recite our Shanti mantra. Asato ma sat gamaya, tamaso ma jyotir gamaya, mrityorma amritam gamaya. Om Shanti Shanti Shanti. From untruth, lead me to the truth. From darkness, lead me to light. From death, lead me to immortality. Om, peace, peace, peace. Okay, let's move on. Uh, so, today's class, we have structured it in this way. We'll do a recap of the previous class for people who are not able to make it. We will then wrap up this the module that we started with, which is evaluation of Bharatiya Astronomy. We will then start with our next module, which is the Bharatiya Astronomical model. Hopefully, we can cover each of these 20 minutes each. If something spills over, we can take it to the next class. And as usual, we will leave a couple of last 10 minutes for question and answers. So that's the way we have structured today's session. Right. So let me quickly recap what we studied or what we went through last time. So we talked about the evolution of Bharatiya astronomy. So we had the earliest astronomical information provided in the form of hymns and poetry and verse and stories. And we also saw that there was a evolution over a period of time to formalizing the rules around the astronomical phenomena. In particular, we saw the different calendars that were formulated, the Panchanga system, and very basic rules like the dividing the zodiac into the rashis and the nakshatras, providing more structure to the observations started happening around the Vedanga Jyotisha era. And then we started a little bit more of a mathematical modeling of the astronomical phenomena. You can see that the Siddhantic works, which we will talk about later, dealt with astronomical events, mathematical treatment of it very rigorously. We saw that certain mathematical formulas and rules were laid out in order to explain this phenomena. And then the advancement in the mathematical modeling only increased with period of time. So when it got to just few centuries back, 4 to 5 centuries back, there were very complex mathematical models that were established to explain the heliocentric model that was being proposed, to explain various phenomena like eclipses, and which it also provided the basis for the very detailed calendars that we are using for our day-to-day purposes in the current era. So the overall narrative has been moving away from glorification of the astronomical phenomena and the gods to an era where it was ritual focused to an era where it was more mathematically uh, formulated, and the advancement continued in that way. We saw a few examples of each of these different stages of evolution. Uh, so, we saw that initially it was more of stories and verses, but then the stories and the metaphors got very strong over a period of time, and they started conveying astronomical phenomena. And then we then got into a very sophisticated mathematical formulation of the different observations that were made. Right? So some examples that are a reference. We also saw that it was a very well structured process, right? So there were observations. Again, I want to emphasize that observations played a very, very vital role in in building the knowledge of astronomy, and hence we our ancestors also devised in different instruments, which we will deal with in a separate lecture, to sharpen their observation. Right, our mathematical tools were also quite advanced in the sense they were evolving over a period of time, rivaling the Western counterparts, if I may say so. And we also came up with theoretical models like the epicycle model to explain why why we to explain the observations that were being made. And the icing on the cake was really the refinement of this entire process, which means, and this is I cannot emphasize this point, overemphasize this point at all, because we were continuously admitting that there could be mistakes, we were refining it, and we were very incrementally building up that knowledge, which which has led to a very good quality of the knowledge that we have today on the Bharatiya Astronomy, right? I've just listed down a few equations that we were actually dealing with in the 1500s or 1600s, which seem as scary as the equations that we have learned in school. But this was the level of mathematical advancement that we were dealing with at that time, right? So this is what Parameshwara had, who was one of the leading Kerala school astronomers, had beautifully captured in this statement. In course of time, let other corrections be thought of by the foremost of astronomers, because after a few years, the correctness of my parameters is not certain. So there is always an acceptance that there is a room for improvement, and uh, the fact that whatever a particular astronomer is saying is not final, right? It's subject to improvement over a period of time, right? Because over a period of time, the observations will also change, and new theories or new hypotheses may have to be postulated to correct the knowledge that was prevalent at that particular time. So this is just one example. There are several other quotes across our body of knowledge which uh, has these kind of disclaimers, right? To say that what I'm saying is not really the gospel, but it is subject to correction over a period of time. So we'll deal with it hopefully, more as we go by. Then we talked about the Vedanga Jyotisha, right? So the Vedanga itself is the six limbs of the Veda, as is listed here. Yeah, Jay?
No, I just want to emphasize exactly what you told, that there was such an emphasis on the humbleness of the knowledge gathered by the ancient Indian astronomers, and ancient Indian knowledge systems in general. Because if you look at the current scientific world, which I'm a part of, it's very hard to actually dislodge any particular theory that exists. So, for example, if someone wants to prove against the Big Bang theory by introducing a different perspective, That is extremely hard to do because the entire scientific community and the peer review process is so entrenched, and it's so hard to actually bring out a new theory or destroy the current theory. So that I'm not, so you should look at the ancient Indian systems. It was not so difficult to do because if you look at the different examples of people throughout the time, you can actually see people argued very much against each other, and it was a part of the process. And the humbleness of the entire process also was something important. Yeah. So
Yeah.
sorry to
And
interrupt.
no, thanks, Ajay, for adding that. Again, like I said, we can never overemphasize that point because that's like a common pattern that we see that the continuous challenge. For example, like we discussed last time, Brahmagupta fiercely challenged Aryabhata. Aryabhata was the pioneer of Indian astronomy, right? But then Brahmagupta never accepted any of his theories, right? Uh, and then he set out to actually uh, uh, formulate his own theories, right? Which then led to the next level of advancements and so on and so forth. And we will also see as we go into the astronomical model again how there are several points of view on the same subject, which is really essential for the advancement of that subject. Right? So we'll talk about that. But thanks for that, Ajay. So we then saw the Vedanga. Vedanga. So we are now moving to a different era, right? From Puranas and Itihasas uh, to the Vedanga Jyotisha era, where the ritual or the yajna was at the center of everything. So in order to do the yajna, our ancestors needed the right time, the right place uh, uh, to perform the yajna. So they needed precise calendrical computations, right? So that necessity spawned a good body of knowledge, which we call it as the Vedanga Jyotisha. Uh, and especially it dealt with three aspects, right? Ganita, Samhita, Hora, like we discussed last class. Ganita is the complete computational basis for the Vedanga Jyotisha. Samhita and Hora are more predictive nature, right? So, for example, predicting natural disasters or predicting agricultural produce for an year, right? Or Hora, which is more individual uh, kind of prediction centered around an individual, like the individual's education, marriage, longevity, and so on and so forth. So today's world, Samhita and Hora are what is loosely classified as astrology, whereas Ganita is still goes by the name of mathematics and astronomy. However, in those days, the distinction was not there. It was primarily one body of text that was addressing both the concerns of today's astronomy and astrology, right? But then, of course, the focus of our course is going to be the mathematical astronomy, uh, spherical geometry, planetary systems, and uh, all that aspects. And we will not go into the predictive aspect. Right? So we saw that. So we saw all that, and then we then talked about. Okay, so now we are in the Vedanga Jyotisha era, right? Now, when did Vedanga Jyotisha uh, come into being, right? So the Vedanga Jyotisha is dated uh, as a continuation of the Vedic period, right? So there is a lot of debate around when this happened, but and there are several, as you can see, several estimates as to when the Vedanga Jyotisha was written. Some as early as 1400 BC, like S.B. Dikshit is pointing out, some as early as 500 or as late as 500 BC, as Weber is pointing it out. Uh, so the other Indian scholars, such as Balagangadhar Tilak, Vaidya, favor a date that is much older, whereas many Western scholars typically uh, argue for a much newer date around the 500 BC. So why is this disagreement there? See, one thing is all of these dates are backtracked based on the references that are present in Vedanga Jyotisha itself. So Vedanga Jyotisha makes note of certain astronomical phenomena. Now, then we kind of extrapolate that back in time to arrive at a date. Now, because the interpretations can actually be different, uh, the dates are also different. Specifically speaking, there is a phenomenon called precession of the equinoxes, which we will deal with in greater detail. However, the disagreements in the idea and the time frame of the precession can offset these dates by a significant amount, and that's what we are actually seeing it. Right. The interpretations of the texts of the slokas present in Vedanga Jyotisha, it causes these variations. Right. Now, uh, yeah. So we talked about that. So generally, the current understanding is it's somewhere between 1200 to 1000 BCE, accepted for all practical purposes. And But what is more important is not the fact that Vedanga Jyotisha was formed on a particular year, on a particular date, right? But it's a rather a living tradition, right? That kind of, or this way of thinking, or this school of thought, which placed the yajna at the center of it and was formulated to facilitate the yajna process, uh, came into being at around 1200 plus or minus 100 years BCE, and it continued to be updated and transmitted uh, to the future bodies of knowledge, right? So, yeah, it may seem that there's a lot of confusion between these astronomers, but then it's also a complex problem where agreement is quite tough, right? So, it was originally authored by a person called Lagada, right? So Lagada probably compiled the text, but then the text was continuously updated by others as well. However, Lagada is kind of correlated with the Vedanga Jyotisha. Right? So it's a very brief history of Vedanga Jyotisha per se. And now let us actually look at some verses from the Vedanga Jyotisha, right? Particularly, I want to draw your attention to the second verse, which says, the sun and moon start moving north at the beginning of Sravishta. The sun starts moving south at the middle of Aslesha, and this always happens during the months of Magha and Shravana, respectively. So, this is an example of an astronomical marker present in Vedanga Jyotisha, which gives us a clue as to the time or the antiquity of the Vedanga Jyotisha. Right now, in order to understand that, one should also be familiar with the nakshatra system of the zodiac, so which is presented here. Now you can see here that so this is the 27 nakshatras, right? So if you look at if you go and look at the night sky, uh, it's so the night sky makes that's a 360-degree circle that the zodiac makes, right? Or the path in which the sun, moon, and the other grahas travel. So that 360-degree portion of the sky can be divided into 12 rashis and 27 nakshatras. And you may be familiar with these nakshatras, which start with Ashwini, Bharani, Kritika, Rohini, Mrgashirisha, so on and so forth. Right. Uh, Now, during the time of Vedanga Jyotisha, summer solstice happened happened when the sun was transiting the midpoint of Aslesha. Right? Aslesha is present in the Kataka Rasi. And the winter solstice happened at the beginning of what we call Sravishta or Dhanishta, right? Which is present in Makara and Kumbha, right? Or rather, the starting of Dhanishta is present in Makara, right? So, using this information, uh, the uh, the astronomers were able to backdate as to when the Vedanga Jyotisha was written, right? Uh, so, I mean, so why? So, what is the purpose of this, right? Or what is the significance of this, right? See, this line, so of course, this is a virtual line that cuts the Aslesha star and the Dhanishta star, where the solstices happen. It is not a constant with time. It keeps oscillating depending on the precession of the earth, right? So the precession of the earth is a phenomenon by which uh, the earth not only rotates on its axis, not only rotates around the sun, but it is also spinning like a top, that wobbly motion that a top, I mean, if you have ever seen a top that is spinning and it is coming to a stop, it exhibits a wobbly motion. In that wobbly motion, the axis of the rotation keeps oscillating until the top actually comes to a stop, right? So that wobbly motion is called precession, and that wobbly motion causes the solstice points to change with time. Right? We will talk a little bit more about this in detail, but for now, just absorb this fact. So, uh, so now based on the precision calculations and based on the information that's provided, is how our ancestors arrived at, or the research, the scholars arrived at these dates, right? So I just wanted to showcase how this is kind of done. Uh, this summer solstice, of course, you might also know what solstice is the longest day in the north. Summer solstice is the longest day in the northern hemisphere, where the duration of the day is, or the difference between the duration of the day and the duration of the night is maximum. And the winter solstice is exactly the opposite, where the duration of the uh, night is much greater than the duration of the day, and it is maximum as well, right? All of this is for the northern hemisphere. For the southern hemisphere, again, this reverses. So the southern hemisphere has the summer solstice in December and the winter solstice in June, right? So typically, for us, right, in India or in the US, we are all north of the equator. Europe, so we have the summer solstice around the June 21st date, and the winter solstice during the uh, December 22nd date, right? And if you draw a line that is perpendicular to this, maybe it cuts through Swati and Bharani here, that will be the points where when the sun transits, the equinoxes happen, right? Which means uh, the vernal equinox or the spring equinox could happen at, say, Swati or Vishaka, where the day and the night are of equal duration. Similarly, Kritika Bharani could see the autumnal equinox happening, where the day and night are of the equal direction, right? Also, of the equal magnitude, but the direction is from longer days to shorter days in this part, and in this part, it is from shorter days to longer days, right? So, just wanted to show this shloka from Yajush Jyotisha. Right? So, see, the main takeaway from this is that see, there are precision of the equinoxes has been identified. It was known. It is also documented, right? Which we will see in much detail before, right? Now, okay. So, quick question: Can you take a guess as to what this red line could be? Anyone? So remember that the solstices happened in these nakshatras at the time of Vedanga
This is
Jyotisha.
Kartikai, Paurnami.
No.
Could
Okay,
that
so
be
Is
the
it like
start of the year?
currently this is happening now?
The winter summer solstice happens at this nakshatra.
Correct. That is correct. That is
Yeah.
correct. So this is so. See, the amount of precession of the earth that has happened from the Vedanga Jyotisha time to the current time is this extent, right? So today the summer solstice is happening in Mrigashirisha, and the winter solstice is happening in Mula, right? Now, let me take a quick detour to. Okay, so this is a software called as Jagannath Hora. It is used. It's a very famous tool used by astrologers. It's very user friendly and it has all the information that you want to do predictions, right? Now I've set a time of June 21st, 2025, typically when summer solstice happens in the northern hemisphere. You see
Madhu,
where?
we can't see your screen.
Oh, sorry. Okay. Sorry. I need to reshare my screen, I think. One second. Let me share my entire screen. Okay. Can you see it now?
Yes.
Okay. So this is Jagannath Hora. It's a basic astrological software. So here I have set a date of June 21, 2025, which is when the summer solstice happens in the northern hemisphere. And you see where the sun is present. So the sun is present at Mrigashirisha, fourth pada. And it's about to transit to the next nakshatra, which is Ardra. Right? So you see that the sun is here. Similarly, if I set a time of December 22nd, which is when the winter solstice happens, right? You see that the sun has moved exactly 180 degrees and it is now present in Mula Nakshatra. So this is Mula Nakshatra. Right? So today the solstices are happening at Mrigashirisha Mula axis. Right? Now, whereas on the day of the Vedanga Jyotisha, it was happening around the Dhanishta Aslesha axis, which is somewhere here. So Dhanishta is here, Aslesha is here. So it was happening in this, right? Now, as time goes by, this line keeps moving, oscillating back and forth. And by the way, this is a cyclical oscillation. There's a fixed time period for this. We will talk about that later. But then, as this line moves, the months or the times when the solstices and the equinoxes happen will also keep moving. Right? So this is what is called as the precession of the equinoxes or the precession of the earth, which is caused by the wobbly motion of the earth. Now again, what causes precession? There are several theories. Typically, see the earth is also subject to multiple gravitational forces on different directions, like the sun is there, the moon is there, and then we have large bodies like Jupiter and Saturn. Now, the resultant pull from these different planets causes this wobbly motion to happen. And the rate of precession or the time period of precession is typically understood to be 26,000 years. So, what do we mean by that? What we say is today in 2025, if we are seeing that the solstices are happening in Mrigashirisha and Mula axis, which is this axis, then after 26,000 years, again we will have the solstices happening in the same nakshatra. Right? By that time, it would have oscillated to other parts in the zodiac before it comes back to its original value. So 26,000 years is the time period of precession. So let's talk about precision a little bit more detail. I just wanted to convey how Vedanga Jyotisha itself talks about its antiquity. So that was the point. And incidentally, we went into the Jayavara software for that. Right? So that is that. And we also touched briefly upon this Nakshatra Mandala, which again is very core to our Indian astronomical model, and which we will deal with in a little bit more detail, going forward. Right? Okay, now, yeah, Ajay.
Same thing. I think you're now not sharing the right screen because you can see your notes.
Okay, one second. Is it fine now?
Yes.
Okay, perfect. Okay. Okay. Fine. All right. So, okay. So just to wrap up this, right? Now, after Vedanta Jyotisha, we are moving to the Siddhanta era in astronomy, right? So, the Siddhanta era is, we can conveniently call it as the golden age of Bharatiya astronomy because, again, from the Yajna being the main factor behind the development of Vedanta Jyotisha, we are now doing or achieving a quantum leap in our computational capabilities, right? So several siddhantas are postulated, right, over a period of time. So there are totally 18 siddhantas that were authored between the 3rd and the 12th century Common Era, which is which Kashyapa Samhita is, highlights of Surya, Pitamaha, Vyasa, Vashishta, Parashara, Kashyapa, Narada, Garga, Marichi, Manu, Angirasa, Lomasa, Vyasa, Yavana, Chavana, Bhrigu, Saunaka. Right? Now, unfortunately, we have lost all these Siddhantas for reasons unknown. However, we do have the Surya Siddhanta retained, and Surya Siddhanta is the crown jewel of the Siddhantas, right? It's a very foundational text that has a very complex mathematical treatment of astronomy. It includes several algebraic equations and trigonometry and even early what do you call early uh, notions of calculus, which formalized much later. And the purpose of the Siddhantas was no more rituals, right? We were now going into an era where we want to formulate rules, models, and back it up with mathematical formulas, right? So that's the hallmark of the Siddhanta era, Surya Siddhanta. So there is a different school of thought that there are two versions of the Surya Siddhanta. It's called the Surya Siddhanta and the Saura Siddhanta. The Saura Siddhanta is not available today, but Surya Siddhanta is the, let's say, the updated version of the Surya Siddhanta that is popular today. And so, how do we know that these Siddhantas exist? Because we do have references in other texts that came later to these Siddhantas, but the original texts, Siddhantic texts, were actually lost. Only the references remain, and that's how we know that these Siddhantas were there in the first place. Now, Varahamihira, who was again a very, very influential polymath, like he's not even an astronomer, he's like a multi-talented multi-talented artist of his times. He compiled these 5 Siddhantas, Surya, Vaitamaha, Paulisa, Vasishta, and Lomasa, into what is today called as the Pancha Siddhantika. So it's a compendium of 5 different Siddhantas. It's a very, again, it's a very often referenced body of work as far as Bharatiya astronomy is concerned, right? So this Lomasa, or what is called as Romaka Siddhanta, incidentally, as you can guess by its name, was actually adapted from the Hellenistic or the Greek influence as well, right? So this showed that our borders were literally not closed, right? We were adapting from uh, the West similarly, and we were actually integrating and we were absorbing the discoveries of the West into our Siddhantas also. And at the same time, we were exporting knowledge to the West as well. So that mutual exchange of knowledge was happening in those times, right? So these are the Siddhantas. I'm just going to do a quick time check. Okay, we have time. Okay, now this is yeah, we can call this as the not. It's not really right to say it's the post-Siddhantic era. It's still we are in the Siddhantic era, but then again, this is a golden period of Bharatiya astronomy where we have several influential uh, astronomers coming up with their research and bodies of knowledge. Aryabhatta, of course, is a prominent astronomer, and he has. So the Aryabhatta is famous for his Aryabhattiyam, which is a very small text on Bharatiya astronomy. Right. However, there are several commentaries and several bhashyas that are written on the Aryabhattiyam. So it was almost acting like like it was the foundation or the fountainhead of several other works that came later, right? So you can see concepts like spherical geometry and algebra, rotation, formulas that govern the rotation of the Earth, how eclipses are calculated, the formulas for that, the mathematics. So everything is seen in Aryabhattiyam, right? And Arya Siddhanta is also another not very well known text, but Aryabhatta is. So by the way, this is Aryabhatta 1 because there is another Aryabhatta that came later down the line as well. And I just want you to make note of the fact that Aryabhatta has only one T, not two T's, as is often misconstrued. I'm guilty of making that mistake in the past as well. So that is Aryabhatta. So this was around 476. Right? And then we have Varahamihira. He was from Ujjain, and Varahamihira was so advanced of his times that he was the first one to provide a method to solve a first order indeterminate equation, right? So equations of the form ax plus c is equal to by, right? So how are these solved? He was the first one to provide a solution to this equation where, if I'm not wrong, the number of variables is, or see the number of, I think not, so you don't have as many equations as the number of unknowns. It's like that, right? So it's difficult to solve such problems, but Varahamihira actually came up with solutions for that. And as we saw earlier, Pancha Siddhantika is a compilation of the different Siddhantas. And another magnum opus work of Varahamihira, or rather his actual magnum opus, is the Brihat Samhita, right? So the Brihat Samhita is, if you recollect earlier, we saw that Samhita is about making predictions around events that affect large masses of population, right? Like weather forecasting and natural disasters, eclipses, things like that. So it so there was both astronomy and astrology kind of intertwined into Brihat Samhita. Not only that, he didn't stop with astronomy and astrology also. There is a lot of other shastras that are part of Brihat Samhita, such as Ratna Shastra, which is gemology, right? So uh, what gems are used for what purposes. There is Super Shastra, where he talks about how different items have to be cooked, right? Different kinds of rice that has to be used for different purposes, right? And then Bhugarbha Shastra, which is known as geology in the modern day. So it is a, it is a very broad area, broad text that encompasses multiple uh, fields of science and arts as well, right? Uh, Varamira also, by the way, was a fantastic mathematician. And if you get time, you can look at his work on magic squares, right? So magic square is where, if you add all the numbers vertically or horizontally or diagonally, you could arrive at the same sum. Uh, Varadara took it to a next level by actually saying if you actually fold this piece of paper and if you add, it comes to the same sum, and he made a lot of advancements there. Now, the beauty of this is not so much as in doing the magic square itself, but the fact that this was done for a practical purpose, right? So, for example, making of perfumes was was one of the arts in those times, and Varahamihira was experimenting the different proportions in which the same perfume can be made, and he was using the magic square as a tool to do that, right? So it was almost like Newton inventing calculus, because not inventing, he was discovering calculus because he wanted to explain gravity, something like that. So I see Mahesh has raised his hand. Mahesh. Maybe you're talking on mute, sir.
I'm sorry, I was on mute. In this slide, what is the difference between the top row, which is in blue, and the orange at the
No,
bottom?
there is no difference. It was just that I was not able to represent the entire timeline in one linear row. I kind of split it as between
Oh,
500 to 1000 as one logical part, and 1000 to the current era as another logical part. That's nothing
okay.
beyond that. Yeah.
Okay, thank you.
It was just for convenience. Yeah.
Okay, thank you.
Okay. So we then move on to Bhaskara. Right now, Bhaskara 1. Again, there were two Bhaskaras. Bhaskara 1 was a ardent disciple of Aryabhata 1. So he believed everything that Aryabhata said, and and he wrote commentaries on Aryabhatiya. Like I said, there were many commentaries written, and Bhaskara 1 wrote probably the earliest and one among them. And then he also had his own works called as Mahabhaskariyam and Laghu Bhaskariyam. Again, he provided a detailed method for solving what we today know as linear Diophantine equations or first order indeterminate equations, right? So there are, in particular, he provided a certain method called as the Kuttaka or the pulverizer method, is like literally pulverizing the equations to get the solution, which is to find integer solutions for equations which are of the form ax plus c is equal to by, where a, b, c are integers and x, y are unknown integers, variables. Right. So you are seeing that the level of mathematics, even at 600 current era, is astonishing, to say the least. And these are all used not for theoretical modeling, right, but for as a basis for astronomical computations of planetary motions and eclipses and things like that. So such was the greatness of these astronomers. And then we go over to Brahmagupta. So Brahmagupta was a fierce critic of Aryabhata. But he has several slokas that critique Aryabhata, and he took it upon himself to explain the astronomical concepts and mathematical concepts in his own way, ideologically contrasting with Aryabhata. He was the author of Brahmasputa Siddhanta, which is again his magnum opus. And by the way, I think some of you already might have enrolled into the Brahmasputa Siddhanta course, which is a very intense mathematical treatise, where he has now taken up this mathematics to a different level by solving second order indeterminate equations. Not only ax plus b is equal to cy, but he's talking about ax square plus bx plus c is equal to something, right? He has dealt with the concept of zero, the concept of negative numbers, and everything for as the basis for astronomy, right? So he has authored another work as well. Then we go to Vateshwara. So Vateshwara talked mostly about planetary models and furthermore refinement to the mathematics. And then we have Manjulacharya, who wrote Laghu Manasam, right? Now the Laghu Manasam, the beauty of it was he just simplified all these mathematical calculations and everything, and he provided a very concise manual which can be used as calendar. So today, when we refer to the Panchanga, we don't go into how this was calculated. Or today, even when we see horoscopes in astrology, we don't bother about computations, right? We just take the information. All this information is condensed, all the mathematics is done behind. He has provided it in a very practical way that can be taken and used for the day-to-day practical needs, right? Manjulacharya also has the credit for refining the eclipse calculations, right? So when eclipses were calculated during those times, the rest of the world was taking you need to know the angular velocity of the moon in order to say that the eclipse will last for so much duration, right? So everyone was taking the average angular velocity of the moon. However, Manjulacharya was one of the first to say that you have to take the instantaneous point in time angular velocity of the moon, and thereby he made the eclipse calculation little bit more accurate, right? So that was one of his big achievements, and he also dealt with a lot of trigonometry in his text, right? And then we have Aryabhatta too, who was another later astronomer, not very well known, but then he also built upon the knowledge of Manjula on the calculation of eclipses and the planetary positions. And then we have Bhaskara too, who is again a groundbreaking Indian astronomer. Not only was an astronomer, he was a great poet as well, right? So he was blending astronomical science with art in his works, like Siddhanta Shiromani and Karana Kutuhalam, right? Siddhanta Shiromani obviously is his magnum opus. It's a very bulky treatise on astronomy. So he wrote several theories on planetary models and other mathematics underlying that. So he is also the author of another text called as Bijaganitam, which again builds upon the work of Brahmagupta's work on second order Diophantine equations and provides a different method for solving the Diophantine equations, right? So there is an interesting anecdote about Bhaskara too solving Fermat's problem, right? You might want to look it up, or probably I'll send a link to it in the WhatsApp. So Fermat was a European astronomer who had posed a certain problem, which was actually taken up by Bhaskara as a challenge, and he solved it. It's a very famous one. 61y square plus 1 is equal to x square, the solutions for that equation. Right? Bhaskara too is also the author of Leelavati, which is a little bit more fundamental text on algebra and geometry. Right? So I'm just giving an idea of the level of advancement that we had in our, in these years of around 1,000 common era itself, right? Now, you see that there's a big difference between 1,000 and 1,400. I don't know, maybe some invasions happened in North India and certain texts were destroyed or whatever the reason was there. Not much advancement happened, or it's not available to us, either of these things. And there's a clear pattern now that we see where the focus of astronomy expertise is moving from North India to South India. So if you see, most of the astronomers that are coming after this are from the Kerala school of astronomy and mathematics, right? One of them is a person called Madhava, right? Madhava, you might have learned about him, is the first to use infinite series approximations and also to find the value of. He also found the value of pi, which he has codified using some slokas. We had Parameshwara, again, very famous Kerala school astronomer. So Parameshwara, he has observed 15 plus eclipses in his 55 years, and he has continuously refined his calculation of eclipses based on these observations. And he traveled as far from Kerala to where Gokarna in Karnataka is today. I mean, today, of course, traveling from Kerala to Gokarna is nothing. But in those days, when people were following all the acharas and travel in general was very tough, he actually undertook this journey just to observe eclipses. Shows some kind of commitment and professional ethic, right? So he was very prominent Kerala school astronomer, and he has several other texts, and he also has a commentary on Bhaskara, which is called as Mahabhaskariya. So Parameshwara, and then we had Nilakanta Somayaji, again another very pioneering astronomer, Tantra Sangraha. Right? Tantra Sangraha is a magnum opus of Nilakanta Somayaji. He also has a Bhashya on Aryabhatiya, and Nilakanta is actually a grand student of Parameshwara. So he was like, Parameshwara was his guru's guru, and Nilakanta is famous for advancing the planetary model, right? So he almost suggested that there is a heliocentric model, although he didn't say it in so much words. He said that the other planet, so he said that the Earth is orbiting the sun is orbiting the Earth, and the other planets are orbiting the sun. So he was the first one to propose to move away from geocentric model to a heliocentric model, but then he did not say it in the way we understand heliocentric model, that all planets revolve around the sun, but he was the first to kind of broach that idea in the astronomy circles, and it's called as quasi-heliocentric model today, right? So Nilakanta is famous for that, and then we have Ganesha Daivigya, who was from Maharashtra. So at that time, there were many Maharashtrian astronomers who were moving to Varanasi and studying in the universities there, and so there's a lot of exchange happening between different parts of India or Bharata at that time, right? So again, famous for simplifying the Panchanga for us, refining and simplifying the Panchanga. And then we have Jyeshta Deva, again Kerala school astronomer. He compiled Yuktibhasa, and Yuktibhasa has calculus-like concepts in it, much before Newton, at least 2 to 3 centuries before Newton came. And then we have Chandrasekhar Samanta, who was from Odisha. And Chandrasekhar Samanta, his uniqueness was the fact that he built his own instruments. Of course, at that time there were no telescopes, but then he built his own instruments to calculate the angular distances of planets and eclipses, and he used that to refine the calculations and slowly building upon the knowledge that was there before that. And we have other schools, Shankaravarman from Kerala again, Venkatesh Ketkar, we are now almost coming to 900 Common Era, is almost like a modern day scholar from Maharashtra. So you can see that there is a continuous cycle of innovation happening for the last 1,500 years, slowly building upon the shoulders of the giants and getting it to a stage as to where we are today. And and each of them have had their role in advancing the study of Bharatiya astronomy. Now, obviously, this is a very small talk about the different astronomers. We will have a separate session, hopefully, where we can go into the detail of the actual works and how they have dealt with astronomy and mathematics, right, in their works, hopefully at a later point of time.
Madhu, I think the only
Yeah.
Few minutes left, 5 minutes
I
left.
Yeah, I will just wind it up with just one more slide. I just wanted to quickly show this. Let me know if you're able to see my browser opening now. If not, I'll stop and share again.
Not yet.
Okay, okay. So let me share it again. Okay. Okay. So this is like a quick infographic, right? I hope you're able to see it now of where the different astronomers live. And as you can see, there's we're almost like a equal spread of astronomers in the east, west, and north of India. You have this is Vateshwara, who is now who was in present day Jammu and Kashmir. We have Chandrasekhar Samanta from Odisha. We have Bhaskara from Gujarat. Of course, we have the famous Kerala School of Astronomers. So the knowledge was kind of not limited to certain geographical areas. It was happening, the research and the advancement of the knowledge was happening across the country. And there was also exchange of information happening. So a lot of Maharashtrian astronomers, like I said, traveled to Varanasi, where they studied and they brought back the knowledge and so on and so forth. So I just wanted to give a quick overview of that. And if you are interested further in reading about detail, you can refer to this book, Indian Astronomy by this Balachandra Rao. It specifically deals with the progression of the astronomical knowledge through the Siddhantic era, right? So, yeah, so that is another aspect of it, the geographical spread of the knowledge. And so that is pretty much what we wanted to cover, as part of the timeline and the antiquity of astronomy over the years, right? Or over the centuries, I should say. I have a very easy and quick assignment which I will publish. It's just asking some questions from what we have learned in the last two classes. I've just done a small color coding to show the.
I think you're still on the browser.
I don't know why. I'm sharing my entire screen, but anyway. Okay. Yeah. So it's a very easy assignment that I've just. It's a multiple choice question. You can even answer it from the PPT that is there, and just a small color coding to indicate the difficulty level of these questions. All of them are very easy questions, so you can just complete them, right? And share. So that is basically what we wanted to cover in this session. Any questions, comments, suggestions? Please go ahead.
Harini had her hand raised.
Namaste. Can you hear me?
Yes.
Yes.
Yeah, I just wanted to add that there were some mathematicians, especially after Bhaskara too, like there was Narayana Pandita, who has done a lot of work on Ganita Kaumudi. It is actually, the text has been found in the past few decades, and they are correcting it at IIT Bombay. So that is one thing I wanted to add. So
Sure.
it is not totally there is not a huge gap there. And then there was Sridhara, Sripati, Patiganita, all these books were there.
Okay.
Other thing was there is in Jain University currently there is a work by Dr. R.N. Iyengar, who has found the Vedanga text on Vriddha Gargiya Jyotisha, which he dates it back to almost 1800 BC. So even before, or it was a part of Vedanga Jyotisha, or it was before Vedanga Jyotisha, I'm not sure, but it's called Mahasalilam, and recently the Central Sanskrit University has released a book on it. So.
Okay. Yeah, thank you. Yeah, I think, see, the idea was to, I literally not go into the level of detail with all the astronomers and contributions, but more to provide a timeline of the evolution. So I
Yes,
might
yes.
have missed a few of them.
No, it was from 1800 BC. He actually states then exactly the sun was divided into 12 Adityas, that is 12 months. And also when the celestial sphere was divided into 27 nakshatras. So it is detailed in the Mahasalila. So it is before even the Vedanga Jyotisha.
Okay,
Yeah.
sure. Thank you for that information. So Ajay will have a class dedicated for antiquity of Indian astronomy that's coming a few classes down the line. So we will hopefully plug these gaps there. That this was just to provide a see, because we cannot understand, or we cannot put into perspective of the astronomical model until we have at least a high level uh, knowledge of the timeline of the evolution of astronomy, right? And that was the purpose of the last two classes, right? We will be quoting different slokas. Our mind will be thinking, hey, is this from 500 years back, or is this from 1,000 years back? Or are we talking about Vedas and Puranas? So intent was for us to have that perspective that we had these kind of last two classes. So with this, I think we are ready to move to the core, which is the astronomical model, where we will deal with the concept of spherical geometry as well as the reckoning of time. Right? What does time mean in Bharatiya astronomy? What does space mean in Bharatiya astronomy? We'll touch upon the core, and hopefully this knowledge will come in handy when we get there. So I think that was the intent. Thank you very much for that. Any other questions, comments? Ajay, do you want to add anything?
No, I think everything was excellent. Basically, Madhu will be continuing with his portion next week as well, and then it'll be much more, I suppose, in detail in terms of intensive from a mathematical perspective as well. So yeah, I'm looking forward to that.
Yeah, and I will share this deck in the Google Drive. I hope you're all able to access that drive. I will share it. It has the assignment as well. It's a very easy assignment, just for you to refresh your knowledge on it. You can submit it, and we will go to the next module from the next class onwards. Thank you very much.
I have not
Thank
been able to
you.
access the Google Drive.
Okay. Is everyone else able to access it? The PPTs that we shared.
Yeah,
I
I
have
think
others.
I was able to access.
Okay.
Yeah. So let me know, madam, what is the error that you are getting? Because we have just.
I can send you a screenshot.
Yeah, please do that. We expose that to everyone.
As long as the email is listed, it should be okay. And you have to access it from the email it was sent.
Yeah.
That's how he gives the access.
Yeah. So. Yeah.
Okay.
Okay.
Okay. Thank you.
All right then. Thank you for today's class, and we'll meet next week at the same time. Thank you very much.
Thank you. Namaste. Thank you.
Namaste, Hari Om.
Right.